Okay, last round, and now looking towards the future. We have three speakers in this panel discussion: Chip Elliot, Nick McKeown, and Paul Saffo, who will present in that order. Chip has been at BB&N for longer than he wants to admit, and is now responsible for managing the Genies program, which is part of the National Science Foundation's initiative to help support research on possible future internet architectures. Chip, I'm not going to go into all the other background that you've got. You feel free to do that if you want to, but what I'm more interested in finding out is what you want to tell us about Genies. So let's go there.
Well, thank you very much. It's a pleasure to be here. And I should point out we have two of the Genies instigators in the crowd here. So Guru and Nick. Well, I hope you'll jump in, and you know, it's already going that badly. It's like. Okay, I have really only a very, very few slides. I'm kind of just trying to open a discussion about what would be interesting and useful things to do, but I'd like to give you just a little status update about where we are. It's a pretty non-technical talk. This is the space that Genies is trying to open up for research. And so, you know, all of us nowadays live in the internet, whatever that means, right? We conduct our lives, all parts of us are in the internet. And I think it opens up a number of very, very interesting research areas. There are some what you might term science issues, which is it is very, very hard to understand these networks and how they're behaving. Especially if you're a researcher, generally you can't get your hands on any instrumented data. It's very hard to just see what's going on in this space, let alone to kind of have a theory. You know, if you build a bridge, you have pretty good theory about how to build it so it doesn't fall down. If you build large distributed systems, you know, just good luck. I hope you're really good at it. Okay, so that's one area, research that it enables. Another is innovation. And I think for a lot of the academic researchers in particular, there's kind of a sense that, first of all, you know, academia and industry have been kind of drifting apart from each other in this particular space. For most professors, it's very hard to gain any kind of toehold or really kind of make a good contribution in this space. And I think many people have the perception that the barriers are getting harder and harder to enter. In some sense, innovation is being forced higher and higher in the protocol stack because you can't really kind of get in at lower layers. The price of entry is actually very high there. And the third is really societal issues that, you know, we are all, and I think this has come out very clearly in the past day, as we live our lives within this space, this really has very profound effects on society and vice versa, right? So that you can't really divorce the technology and the social aspects at this point. So the goal of Genies is not to solve these problems. It is to open up a space where people can actually try to do useful and productive research and innovations in this space. So here is the kind of the three things that we're trying to do. Let people understand global networks and how they interact with society. So this is not a pure techie gearhead, we need to make optical networks go faster, right? This is much more kind of an understanding of social technical systems. Let people innovate at the frontiers, right? And that's going to be kind of tough to let people in universities all across the US have a way to get in and start doing those innovations. And finally, to transform research. Because right now, a lot of the research is not at all data-driven. There are no instrumented measurements that people can get their hands on. And so if you read a lot of the papers, it's extremely hard to compare one scheme against another. There are no results in some sense. And so this is, to my mind, profoundly unscientific. You would like to have repeatable experiments that are well instrumented so people can actually have a discourse about the facts rather than kind of hypotheses. This is Genies' conceptual design. And the conceptual design was created by kind of a gang of about a dozen professors and a cloud of 100 people around them, of whom I was one of that cloud. I'm sure the conceptual design will change considerably over the next couple of years, but I think this kind of gives, at a sketch, the technological idea. At the top left is the idea of what about a network in which every part, every last little bit of the fabric was programmable. Let's just say user programmable. So we have seen a lot of innovation in the internet space because the edge was open. People could program the edge, but it was really hard to program deep into the network. So what if you could program all the way through the network, every part of it, deep into the network? So that's kind of concept number one. In some sense, let me say, you're kind of loading your application, program, or your service all the way through the network, right? Not just in your end host, not just in the cloud, but everywhere. Number two is, let's try to keep these things separate by using virtualization or the equivalent of virtualization end to end. So from your handheld device, through the base station, through the network, into the cloud, the whole way is kind of one long virtualized thing. In the Genie concept, this is where you run an experiment. So it's called a slice. You're given a slice through the network. You pour your software in. You run it. Hopefully it's well instrumented. You collect your data, and so on. And oh, by the way, a key part of this is lots of real people can start using that experiment. You'd like it to be open because people are very fundamentally a part of what the internet or next generation networks are about. So you can create a long-running experiment and have real people opt in and begin to rely on it. So what we in Genie call an experiment, in the rest of the world is called a service. And this is a way that you can kind of compose new services, start gaining early users, instrument it, see what's going on, and then ideally, if this all pans out, you kind of spin it out as a real service. Some of them, right? That's kind of the innovation path. The third part of this is down at the bottom. It is envisioned as a federated, different kinds of technologies system. So people often, when they think of network, at least where I come from, they think of a router. Well, this one has all the things that you would use to compose kind of a modern global system. Computers, transmission, and storage. And of course, the technologies are going to keep changing, right? They don't stop, so you've got to have some way of constantly incorporating whatever the newest stuff is. So it's a system that's composed out of a bunch of different kinds of things. In the earlier stages, in kind of the conceptual stages of Genie, it was cast as if people are going to think really hard and then build for 5 years and then use it for 10 years. And I think anyone that uses computers thinks, I don't really want to be using a 10-year-old computer system, right? So this has been reformulated as I think the way many of us do things when we're doing big computer systems. We're going to build really fast, rapid prototyping, and use it. Based on kind of what we like and what we don't like, we're going to do it again. So this is called spiral development, for those of you who are into those buzzwords. And each spiral in Genie is 1 year long, right? So everybody get together, make something happen, integrate it, which is very tough, and then use it. We'll try running experiments, and those things we like, we'll do more of. Those things we don't like, we won't do more of, right? And we're just going to kind of keep up, if we can, this forced march. The other major part of this is that Genie is going to grow by gluing together or federating different things. Again, in the conceptual stage was the idea that some organization will be started and will build this monolithic thing. I think that's called Google, actually. That's not the way Genie is going to work. It's going to grow by Genie enabling a lot of stuff that already exists to get up and running, and then gluing more stuff in as the time goes on. An explicit goal is to have things that are not NSF parts of Genie. And so this year, actually, we're starting to federate with European projects, Japanese projects, probably Korean projects, and Brazilian projects to kind of start a shakedown cruise of federation, because that's actually going to be very, very hard, primarily because of the organizational problems. We also envision there are things very much like this probably in the corporate space. And so we would like to be able to federate Genie with those things so that researchers can use some of that infrastructure, probably on some deal basis, back and forth. As new technology becomes available, it will be federated in. So that's the way Genie is going to grow. And there's a little crowd down in the corner that says, well, this looks kind of familiar. I've seen pictures like this actually quite a long time ago. So yeah, this is deliberately copying, at least how we perceive things grew when they were growing well. Okay, here's the current state of the world. Prototyping began about 6 months ago. And so we got very generous donations from National Lambda Rail and Internet 2 of kind of national footprints. So together it comes to, it's a little bit of apples and oranges, but together we've got 40 gigabits of national footprint, which, we're using kind of lightly now. The prototypes aren't really up and running yet. And then we have a number, actually 29 different research teams that are creating parts of prototypes on their campuses. So we've organized this whole thing into 5 competing clusters. So rather than try to integrate 29 different projects, we've organized it so we're integrating much smaller things that are competing against each other. Who can get the most stuff up and running the fastest? And there's 2 basic goals for this spiral one. One is, it's a great idea, this control framework that can kind of create these, virtualization things and so on, but we've never actually seen one of those, right? We haven't seen one. Demonstrate it, right? Produce it and demonstrate it. Goal number 2 is, we love the idea of virtualization and end-to-end slices, but we've never seen that either. So make that work. So in particular, we want layer 2 virtualization, Ethernet level virtualization from, say, campus Wi-Fi through campuses, through regional networks, through these backbones and so on. Once you create one of these Ethernet slices, then you can run IP in it, or you can run non-IP in it, as you like. Or if you like doing minor variants of IP, you can do that. So that the earliest versions of this are now up and running. They were demonstrated in March, and I think we'll have some fairly solid systems by mid-fall. One of the key reasons we want to go to the campuses is that's where the early users are. So we're very interested in getting wireless Genie to a lot of people. Wi-Fi is the first way to do it. We're also very interested in WiMAX because of the spectrum issues. So we would like to have campus WiMAX that starts reaching out and covering the areas around the campuses.
What are the meanings of the numbers on here?
Oh, actually completely meaningless.
Okay,
This is the mapping, and it's an eye chart, don't bother. But they're primarily academic teams, right? A lot of if you're in this field, you've got a lot of the researchers who are busy building and trying to integrate these prototypes. And then we're actively trying to engage companies, because this thing, if it actually starts to be useful, if people actually start running experiments/services, we would like to be able to build it out. And that build-out stage is not going to be done by graduate students. Right? It's just can't be. It's too big a project. So it'll be done by people who are in the business of doing this kind of thing. We'd like to have them engaged kind of from the beginning, right? So if and when we start scaling up, they'll know what to do. They will have contributed to the mix going forward, and so on. Okay, this is kind of my closing thing. This is a very open project. I would encourage everybody in the room to come to the next Genie Engineering Conference. That's July in Seattle. I think this is a real opportunity. For a while, there's been kind of a drift and to some extent a marginalization of networking and distributed systems research in the US. We would really like to start getting people engaged in a much bigger project than they've been doing for quite a while, and with a very heavy industry participation, back and forth between academia and industry. And that's it. Thank you very much.
Any questions?
Oh, I'll take questions now and later. Yeah, Tony.
A few come to mind. Who are the international participants? What kind of sensor applications or platforms do you envision? And lastly, when you use the term federation, you mean that in the identity management sense, in which case what federation platform are you using?
I'm not sure I can remember all the questions in the right order. I'm hampered slightly by the fact that we've just ended a solicitation and we're sending a proposal to NSF on Friday, as it turns out. So I can't say too much about half of the stuff that's going on because it's still confidential. So I'm sorry, what was the first question?
Oh, international.
That wasn't the first question. Oh, it was the first question. So the people who are explicitly identified are, there's a European future internet, quote unquote, project called FIRE, F-I-R-E. I don't remember what that stands for, research and something. That's out of the EU. There's also the Germans who on the national level are doing GLab. So they will very likely become partners. If you drill down even farther, individual places, I won't name them, are actually on some of the American teams. So at several different levels, that's going on. In Japan, it's primarily NICT, which is a quasi-governmental organization. And in Korea, yeah, exactly, yeah. So those are the obvious ones. And then down in Brazil, it's a bunch of regional research networks and the universities associated with them. Sensors. So we have several different kinds. Some are the small mote-like sensors. So we've got a field of about 1,000 mote-like sensors in Ohio and in Detroit, oddly enough. There's several other sensor projects. To me, one of the really interesting ones is actually a big distributed radar system that's doing real-time meteorology. So with a whole bunch of radars. And that's basically not only a source of kind of, fairly substantial volume of information, but they can be controlled. And so, in real time, you can imagine programs that are kind of looking at this data and controlling the radars as well. So it kind of ranges. Federation. So federation here means this is kind of a high level of federation. How does the North American NSF thing interact with the Japanese thing? How does it interact with the European thing? So that's the meaning of federation. If you drill down one layer, how do all these campuses manage researcher identity and so forth? There are multiple competing schemes right now. My personal favorite happens to be Shibboleth, but if you know a better one.
Shibboleth sounds good.
Thank you very much.
So while Nick is getting his computer connected up, he's a professor at Stanford University, and he's been there for actually quite a while, since 1995. He's responsible for managing the Clean Slate program at Stanford, which is basically a program sponsored by the National Science Foundation to look at what an internet might look like if you were starting all over again, knowing what we now know from 30 some odd years of exposure. He has some business background as well, a couple of startups, Abrizio and Nemo. So I think Nick brings a pair of interesting perspectives to all this. One, a practical one from business experience, and the other, of course, a very interesting academic view of starting all over again with the design of an internet-like, or maybe even internet-not-like system. So, Nick, go for it.
That's it. Okay, good. So put this up to start with. I'm going to be talking about something that a term that I stole from somebody else, which is software-defined networking. It follows on nicely from what Chip has been describing. And essentially what we're trying to do is to build a substrate or an underlay to help Chip and Genie happen. It'll be clear that there's a sort of a bigger goal and that everyone is trying to work towards, which is how do we help the network innovate and keep innovating and keep moving forward. And we're trying to put a piece in, sort of an underlay into to help Genie. I put this slide up with the team that we have here. So this is me over here. I'm 6 foot tall. The reason I put this up is just to say that my group is really tall, and I don't understand why. I feel very small in amongst these people. The things I'm going to be describing have come out from a lot of them came from the PhD work of Martin Casado, who some of you know, and he and Scott Schenker and I were sort of talking about this a while ago, and so I'll try and just sort of describe where all of this stuff fits together. But my background was in building the router, in designing routers and trying to make them faster and blah blah blah, stuff like that. And Chip did a great description of sort of the top-down goal of Genie, and we're sort of trying to come from the underneath and say, ultimately, the networking piece needs to go on boxes. It needs to go on the boxes. And the question is, how do you get it there? Because there's a huge number of boxes out there. And if they've all got to be able to support this underlay for Genie, then how do we get that in place? So when I say router, I mean something like this. You all know what these look like. They've got a sort of a management and the routing protocols, the stuff that sits on top, and then the per packet stuff that happens in the forwarding path, the lookup, the switch, and the buffer. And I don't think I'm saying anything that's particularly surprising, but when viewed from the bottom up, I think it's safe to say we kind of lost our way, which is this thing that was supposed to be this dumb, simple data path turned into this monster. Routers today typically have 10 to 20 million lines of source code and you know they're bigger than the 5ESS switch operating systems that we used to mock. They provide a huge barrier to entry for innovation. And on the hardware side, if you take a big router, these numbers are actually pretty conservative. A packet going from one interface to another interface on a big router will encounter somewhere above 500 million gates of processing and encounter about 10 gigabytes of RAM. And this makes them bloated, it makes them power hungry. So this simple thing, this thing that was supposed to be this streamlined data path, has itself become the inhibitor of innovation inside the network. So we tend to think of the network having enabled innovation, and clearly it has, but it itself has become stuck. And on top of that, all of this extra stuff has been baked in, all right, all of these other things. Every single one of them for good reason. We can all think of a good reason why all of this stuff got baked in, but it's made it more and more complex, more and more heavyweight over time. So the question then is what to do. Personal regret, this is me getting my chest clean here. I wish I had said a long time ago. I mean, I'm part of the problem, right, which is part of making these things more and more complex. I used to go to these design reviews for routers, and I used to understand what they did, and then one day I realized that 90% of what they were talking about in these design reviews, I didn't understand the features and the things that were in there. So I wish I'd said it sooner and louder. This dumb minimal data path turned into everything in the kitchen sink, everything piled onto the edge. So the essence of what I want to say is this, that in order to allow innovation happens wonderfully when things are defined in software, right? The open source community, software developers in general, have shown us that innovation can happen at a phenomenal speed with very little standardization if there is a clear path to getting stuff out there, people using it, seeing what works. The bad stuff dies, the good stuff continues, and people adopt it. So there is a hardware substrate that the PC industry has, and I'm really jealous of it. It has this x86 substrate, and it's an instruction set. It's not a particularly good one. It's not a particularly ideal one, but it's good enough, and it's been chosen, or it's been just used and widely adopted. And this allowed software definition to happen on top. The innovation exploded on top applications and in the infrastructure. The thing that we think of as the infrastructure is allowed for huge innovation in the operating system. It didn't for a while, but then alternative operating systems popped up and allowing for huge innovation in the infrastructure itself, operating systems, and then the virtualization layer. And then, of course, open source tied onto the side of that, hundreds of thousands of developers, it's probably more than that, sort of blew apart the whole standardization process. And innovation happened at a phenomenal rate. So, what is it that it takes to do that? Well, hardware substrate, software-defined network, open source culture, boom. Right? This is where we're trying to get us to. I think it's up to us to make it happen. And I think until we or someone does, then the network itself is going to be very hard to change. And I think it's important to come at this from both directions. Top down, driven by the desire to open it up, and bottom up, trying to figure out how. And these two things together gets the problem surrounded. So then the question is, how do you define the substrate? Or do we already have one? Maybe we already have a substrate that's perfectly good. It just isn't being used in the right way. So let's go and look at the computer. The first time I programmed was really before operating systems existed in much of a recognizable way. And when you wrote an application, you took over the whole computer. There wasn't much of an operating system to help you. And so then the operating system came about, and lo and behold, lots of applications came along, because now there was a substrate upon which to do this. So the OS abstracted the hardware substrate, and innovation took place in applications. And then Windows came along, and that sat in the middle on top of what was probably not x86 at that point, but a developing and emerging substrate. Lots of applications. And then there were other operating systems that came along after that, and there's BSD and blah, 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 and, of course, Android as well. But you chose one and you put it on the hardware, but they could evolve and develop because there was this common substrate upon which to develop. So simple, common, stable hardware substrate below. Programmability, people knew how to program because it was well defined. In competitive environment, and it created innovation in the operating system and the applications. The next stage in this, it's a very simplistic view, but the next stage in this was virtualization, VMware, etc. And now not only, you didn't have to choose A or B or C, you could have them all running at the same time in multiple copies, and this obviously creates a phenomenal environment for innovation, not only in the applications on the top, but also in the infrastructure. So here the virtualization and the operating systems, think of that as the infrastructure. This is the equivalent of something to do with the routers in the internet, right? That's the kind of the analogy here, is that infrastructure. Here there are well-defined boundaries, well-defined abstractions. They are themselves changing and evolving. They are defined in software. Innovation is helping improve it all along, and carry it along. So simple, common, stable hardware substrate below, programmability, now a strong isolation model that's being put in place through virtualization. Lots of competition. Innovation is taking place in the infrastructure. Lots of innovation in the operating system and the virtualization layer itself. So it's allowed applications to flourish. What is the equivalent in the internet? Well, the stability of IPv4 allowed the web to happen. There was a stable substrate. Right? That allowed a huge amount of innovation to take place in the application layer. So in the internet, what was it that allowed the infrastructure on top to be defined in software? Well, the routing protocols, the management, there was enough standardization and stability in that you could assume it was there. You could assume that it worked. It allowed the innovation to take. What is it that allowed the rapid innovation of the infrastructure itself? Actually, it didn't. Right, the infrastructure itself has moved. I mean, it sort of had to, and I think we all understand, and it sort of needed to, and part of its success was that it was kind of stable for a while. But that success has turned out to be the problem because it's now very hard to change and evolve itself. So what is the substrate? you might have a picture in your mind. We have that hourglass picture, right? Is it IP? But what is it about IP? Is it the packet format that's the substrate? Is it the packet format plus the IPv4 RFC? Is it that plus OSPF and BGP? And what actually is the substrate? It's not actually clear. We don't have a common idea of precisely what it is that you're programming on top of to allow this to happen. And I think that we've struggled with this in the research community for a long time. And in the mid-1990s, there was I'm sort of paraphrasing here, although I think I took this out of a paper. To enable innovation in the network, we need a program on top of a simple hardware. We need to program on top of a simple hardware data path. This was the mantra of active networking. I'm not arguing that that was a good thing, but it was an indication of sort of a struggle to try and define what this substrate was. Put more fragments of code into the network, let them carry along with packets. That wasn't the right answer. There was a problem of isolation, performance, complexity. What was the stable substrate? It actually wasn't clear what that was, but we're sort of in search of that. The later 1990s, to enable innovation in the network, we need the data path substrate to be programmable. That seems to be getting closer. This is what led to network processors. Well, network processors haven't really happened either. They kind of happened for a while, and then they all got canned, and people gave up on that. Because the thing is, it's a little bit of a cop-out. You don't want quite the same as the x86. You need a little bit more infrastructure than that. No one figured out a common instruction set, a common development environment, and it essentially accelerated complexity of the data path substrate itself. So, perhaps statement of obvious, we've tried this before. I'm not the first person to suggest this. We're not the first people to suggest it. People have been looking for a clean separation between a simple common hardware substrate and an open programming environment on top. And this has sort of been many attempts to do this. And what I'm going to describe is sort of the lead up to one that we've been promoting and working on. Is not to say that we think this is the right answer, but we're trying to move the whole discussion and the debate in the direction of how do we define this simple common hardware substrate. One thing that's interesting is that things are changing fast in data center networks. Whether it's, and to some extent they've already changed in data center networks, whether it's Amazon here or plenty of other places, there's been an awful lot of work because the economics made sense. If you are, let me just offer you some numbers. Imagine that you were building a data center, and imagine that it had about 500,000 servers in it, and imagine that you were building it from switches with roughly 50 ports. You have 10,000 switches. 10,000 switches is an awful lot of muscle and buying power, and when you go out and look at and see that 90% of the price that you're paying is in the software and the margin, etc., there's a huge economic incentive to take it down to the bare minimum, that hardware substrate, down to whether it's $500, $1,000 for the hardware, and use the rest of that saved money to just define it yourself. And clearly that's happening all across the industry, and it's happening in non-standard ways, but it's happening fast and the buying power is tremendous. And it's essentially creating two separate networking industries. There are those who are going with the conventional approach, which I think will be around for a long time, and there are those that are going their own way, and out of sheer necessity and economic pool. And this will create a sort of a very interesting dynamic. What will be interesting is if all the people that are going it on their own can come together. Because if all the people that are going on their own can come together, then this has an enormous potential for change and creating that substrate. So the prior attempts to do this have generally, this is a generalization I understand, either assumed that the current IP routing substrate is fixed and try to program it externally. There have been many attempts to do this. So in other words, provide an interface that sits on top of BGP and OSPF and things like that, and assumes that they are sort of God-given and fixed. And so the routing protocols, which, in the end are kind of part of the problem, right? Because, why is it that my packets are routed the same way that yours are? Why is it that everybody has to use the same thing? This is part of the infrastructure that it itself needs to evolve. We've lived with BGP, the tyranny of BGP, not because it was right, not because it was good, but because it was too difficult to change. And it took a long time, even though there were many problems, in order to be able to change it. And prior attempts have generally defined the programming and control model up front. In other words, they've defined not only the substrate, but how you use the substrate. ATM is an example. All of the effort went in how you describe all the signaling mechanism. Well, what's the chances you're going to get that right first time? Of course it's going to be wrong. You need that itself to change and evolve. Intel didn't define the operating system. It created a simple substrate that allowed many operating systems to evolve and change. So if the substrate itself defines how it's used, that's a path to failure. That can't possibly succeed. So in other words, we need something which is simple, that does not define what goes above. It enables, but it doesn't define. It doesn't constrain what goes above. So I argue that what we need is a clean separation between the substrate and an open programming environment. So a clean separation between the two. A simple hardware substrate that is going to generalize, subsumes, I'm going to come back to this word because this actually seems wrong here. It subsumes and simplifies the current substrate. So how can it simplify and subsume? But it has to subsume, otherwise it has no chance of adoption, unless it is backwardly compatible. That's what we usually call it. That's what subsuming is, right? Unless it's backwardly compatible with what we have, then there's no toehold. It can't get in the first place. And this is really the bane of networking, right? It's the problem that Genies faces. It's the problem that innovation faces. Is how do you at the same time enable and be backwardly compatible? And it must have, that substrate must have very few preconceived ideas about how the substrate will be programmed. And it must have a means for introducing strong isolation. So all of these, there may be more, but these are my short list of 4 needs. I'm going to start with number 1. I'm going to try and be very quick. I'm not going to spend a lot of time on all of these. And at some point, I'll either run out of time or we'll sort of peter out. So the first one is, and again, been said many times before, but I do believe this is very important in networking, is we need to get the intelligence out of the data path. We need a simple hardware substrate in the data path, and we need to remove as much intelligence as we can. Because so long as it's tied into the data path, it's very hard for it to change. So I don't think that the solution is open sourcing the router. People have tried that. There have been many attempts to do that. I don't think that's the right way. I think it's actually to take the intelligence out and then open source the intelligence. That's different. If we can do that and figure out how to do it, after all, this will just be a PC, a server in a data center, or a PC in the closet, then we can put new function into it. And we can do that in software, i.e. new routing protocols, new mobility managers, new energy managers, innovations in the network, but put them, write them in Java and put them on a server somewhere or whatever. So this would allow operators of networks, users, even the application itself, third-party developers, researchers, to be able to add new function into the network. So that's step 1, is separating the intelligence from the data path. Okay, number 2. A simple hardware substrate that generalizes and subsumes. So step 2, once we've removed this intelligence, is how does this control the data path? Well, we need that substrate to be really dumb and simple. We want that substrate to be really dumb and simple so that it gets out of the way as much as possible. So our particular approach is once this controller, this thing outside, this brain, has made its decisions, then just think of it caching its decisions. Just think of it caching its decisions into the data path. It's not giving up its decisions, it's just caching them. And if it can cache its decisions of the following form, I saw this packets that looked like this before, and I decided what to do with those. So if you see them again, do the same thing. And in networking, this is a flow abstraction. I've seen packets that belong to this flow, where flow could be a TCP flow, or it could be all the packets going to China. It could be on a small scale, it could be on a huge aggregated scale. So I mean to encompass all of those definitions of flow. So if I've seen something like this before, do the same thing. So if I can describe it in those terms, then do the same thing again. If header, and this is as simple in the hardware as if header equals X, then send to a particular port or that type of thing. This relies on there being a flow table. And lo and behold, every single commercial hardware switch, Ethernet switch, router sold today has something that looks like a flow table. They didn't put it because they thought of this. They put it there because they needed to implement a firewall. And the firewall has to have access control lists, and the access control lists, lo and behold, they're a flow entry. They say what to do with packets that match a particular flow. So actually the substrate is kind of there already. And it's sitting out there in the wiring closets. It's sitting in the top of rack switches. It's sitting in the aggregation points. It's sitting in the WAN routers. So actually, it's how can we just switch this stuff on? And that's actually, there was the realization for us that not only is it there, but the firewall capabilities are having to improve over time. So those flow tables, they're getting bigger and bigger. There was an immense effort put into building bigger and faster TCAMs. And actually, the TCAM guys are kind of waiting for the rest of us to catch up. It's a little bit of an exaggeration, but they've been working like gangbusters to try and make bigger and faster and lower energy TCAMs. And so the technology is there to have hundreds of thousands of flow entries if we want to use them. And so all of these the pieces come together. And I'm actually going to stop in a moment because I don't want to go over my time. I could carry on talking about this for hours, and unfortunately, many of you have heard me do that, and I don't want to bore you again with the same story. But what we've been doing with this is, from this sort of these nuggets of ideas, we created this thing called OpenFlow, and we have been working to put this feature or this capability into as many switches, routers, access points, base stations as we can. And so we're working with HP and Cisco and Juniper and etc. and getting this put in there. It's essentially the open API into this flow table here to enable this substrate to emerge. And this really is all this thing OpenFlow is. What we've been trying to do, I'm going to actually leap to one last thing. Excuse me if I'm going to go through a bunch of slides here to get there. There's one sort of last point I want to get to. Excuse me. Don't worry, I didn't mean to go through all this. It was, go on. Animations, don't animations suck. If only knew. Oh no, this is when you fall off the end. This is when you, okay, all right, excuse me. I'm going to end at the end. Sorry about this. And in the end, what this is all about for us is getting to this figure here. And that is, the image on the left is of that substrate with the virtualization, the VMware or Zen or whatever, with all the operating systems. What we're trying to do is to get to this point over here where the moral equivalent of that x86 is this thing called OpenFlow. It doesn't need to become a standard, it just needs to get adopted or something like it or better than it, right? We just need something there. We've been developing a virtualization layer that sits on top so that you can then have multiple of those brains that they themselves can evolve and improve and be open sourced or not, that would sit on top. And there is one that's sort of an open source one that's evolving right now, and we hope that there will be more. And then on top, the user, the researcher, the service creator, the routing protocol writer, the network access control creator, all of those will write their application sitting on top for their network, whether it's a data center, an enterprise, a service provider, and that they'll do that outside of the network and on top. Okay.
Could I think it'd be worth explaining what constitutes a flow or what can't constitute a flow, because without any examples, it's hard to grab
Yeah.
the concept.
So in that flow table that sits inside that switch, that flow could be all of the packets belonging to a TCP connection. That would be a legal definition. So I can put in something that says all of the packets belonging to the flow of me going to Google to do a search, right? That could be a flow. Or it could be, if I just change the definition of a flow by changing the bits I match on, all of the packets going to Google from Stanford, or all of the HTTP traffic, or all of the multicast traffic. So in other words, I just mask on whichever bits, and that defines the flow. And I'm free to do that in this flow table.
How much of the packet are you allowing yourself to look at? We're back to potential layer crossing kinds of questions and things like that.
So in the first version of this, we've been trying to work pragmatically with the constraints of the existing hardware. And that generally allows us to look at from the first bit in the packet through to the top of TCP. That's because they have to do firewalls, so they really all need to be able to do that. And so that's a fairly straightforward thing to do that's common to all of this hardware. We're in the process of defining what we hope will be version 2 for about 2 years' time, where we hope that progressive chip vendors and equipment vendors will come along and say, I will now design dedicated hardware because I would like to change the status quo and I would like to do this, where they will allow more bits. And of course, if you match on some earlier bits, like the Ethernet header because it's going over Ethernet, it doesn't mean you have to interpret the higher order bits as IPv4 or TCP. Right. You can define them however you want. So it allows a lovely way to have introduce new protocols at higher layers just by matching. It also provides a very simple isolation model, which is if you think of all of those bits in the headers as representing a space, isolation is just making sure the spaces don't overlap between two experiments. It provides a very simple and strong isolation model as well.
Okay, good. That's helpful. I think other questions before we move to last.
I think Kevin had a question.
Yeah. So on that picture, you said this OpenFlow is kind of like the x86 part, right? And so I guess I would say why not just use the x86 part? Would be one part. But another one is if I want some processing that I need to do that's more complicated, that I think might be more complicated at one of those nodes, even to look at a packet or to decrypt it, whatever, transform it. How do I do that in this kind of model? What's the, if you will, the breadth of the API that you have to use into that switch node?
Yeah. So there were two questions there. Why not use the x86 itself? Well, the starting point today is boxes that process a terabit per second. Right, so that would be a core router. We're quite a long way from being able to do that. We will get there, right, in software. But actually, it doesn't mean that just because one instruction set worked in one domain that it's necessarily the same one. It's clearly the whole numbers and the aggregate numbers are different, right? And that's how the whole ASICs and hardware development sort of emerged for doing that. So that's sort of on the substrate. And the abstraction that seems to make sense is something that's to do with packet forwarding, plumbing. Right, so it's a plumbing layer. So in a sense, what we do is defining the copper pipes to do the plumbing, which takes me to your second question is, what if you want to transform something? Okay. Well, you need a way of steering the flows. We're trying to build the copper pipes, but we're not trying to build the toilets. Right? And the things that then process the packets, you would plumb your flows to it. So let me take an example. Imagine that we build a network like this at Stanford called Ethane. Imagine that you're connecting to that network, and you're a good guy. We've seen you before. We trust everything that you're doing. We just plumb you to the outside world. However, imagine that you're someone new, or you're using some unpatched version of Windows. Then we will plumb you to something that will do intrusion detection. We don't define the intrusion detection. We just plumb it to a middleware box to do that. It might drop, it might transform, it might change. So you can think of it as a way of plumbing to the things that do the transformation. And then, that thing that does the transformation, it could be using x86 processor, it could be a network processor, it could be whatever you want. All we're trying to do is to do the very lowest plumbing layer. That's all. Question in the back?
So it sounds like the classification or the routing would be deterministic. So I'm wondering if there's an option for probabilistic routing. There's many situations where optimal solutions are stochastic rather than deterministic. So I'm wondering if that's available in this system.
Yeah, so one good example of that is load balancing, right? So where you want to load balance over several paths. So in the sort of the version 1, we deliberately chose not to do that because it was hard to fit that onto the existing hardware. That's one of the things that we're currently debating for the version 2, because we agree that there's that's kind of something that you want in there. The question is how to do it in a really, really simple way, so that it doesn't. Our fear is that we don't want to get this to get bloated, right? And then we're back to square one. So how to keep it very, very simple.
So I want to follow up on something that on part of your answer to Vint. In a modern large service provider network, one of the artifacts that you create that maps to this concept of flow is a label switch to path. and you decide at one end of the label switched path what kind of traffic you're going to forward into it. And then you place the label switched path around the network using a variety of mechanisms. There are rudimentary control systems that are very much like what this vision of the shining city on the hill is, in the form of systems that analyze yesterday's traffic pattern and plan tomorrow's LSP mesh throughout a network based on anticipating what the known factors of demand are going to be. I'm hoping that as we evolve this system, we will look back on that time fondly as when we managed the network with bearskins and stone knives.
Okay, good. Thank you.
Any other questions? One more. This will be the last one in this round, and then we need to go on to Paul. Go ahead.
And it's always the last question that brings everything crashing down. So,
I think back in the 90s, right, there was a definition of forces and growth networks and all the thing that happened with trying to define the control plane, separate the control plane from the data plane and try to commoditize this thing. How would you characterize this? How is this different than that approach?
There's clearly been many attempts to do this. You remember Epsilon and IP switching, and there were sort of several attempts to do that. I think there's a couple of differences here. One is, to a large extent, the hardware substrate has already emerged. It's commodity switching and flow tables already built in, right? It's kind of happened. Those things as commodities weren't around at that time. And the second thing is that open source has happened. And so the need to get it all right up front in a spec is no longer necessary. You just need enough to get going, and then bring your friends along too, and enable many, many other people to do so at the same time. And then together you will work at it. Because, the first attempt at Linux, it was just sheer arrogance to try and create a whole new operating system to change the world. And the first version was horrible, but it was the movement that created around it. And the first version of this will be horrible too. Right? They're bound to be. And we'll look back at it and think, how did we ever get started on that? But if you can bring along enough, sort of create that community, then bring along and improve it. And I think the research community that Genies is bringing together is an important part of this. And then there's the open source community that is formed around Linux and Mozilla and et cetera as well. So if they can all be marching in the same direction, wow.
Just to take advantage of the fact that you're walking away, so I'll make a comment. One thing I didn't detect from your discussion is whether and how this particular substrate will help us attack things like scaling problems in connectivity and routing and things of that sort. Is still a big issue. So I'm seeing substrates for experimenting with different packet formats and different ways of describing endpoints and so forth. But this is not a criticism, it's more a question.
Yes.
What do we do about the scaling problem?
Yeah, no, I think that, I think there's two answers to that. One is the complete cop-out answer, which is if we can get the substrate right, then it becomes somebody else's problem to deal with how you program it, right?
Okay, you're right. That's a cop-out.
But the second part of this is that there is an inevitable tendency towards more local separation of the control from the data. I don't necessarily mean centralization. It kind of crudely looks like centralization, but if for example, I take our building at Stanford or the Stanford campus. Our administrators would love it if they can manage the network more centrally, not necessarily entirely in one box in one place. Right? And the thing that enables that is Moore's law, that we have more than 1,000 CPUs on Stanford campus sitting inside switches and routers. Yet you could do everything that they're doing probably inside one $200 PC you could buy at Fry's, right? And next year you'll be able to do twice as much. And put half a dozen of those in the strategically placed locations. Then start programming on top, and people will figure out really clever ways for doing scaling. How you connect those, management and control planes at our campus with Berkeley, with other places. And I think the scaling will come through innovation, right, and through people figuring that out. Yep.
I see Kevin really wants to say something, but we need to get Paul. You can attack Nick privately. I'm sorry? Well, oh, all right. Well, so while Paul is getting ready.
So, and it's maybe it's quickly answered, but the routing scaling problem. We hear this a lot. But when I push the next layer and ask different people I know, what is the routing scaling problem? You never get the same answer. Yeah.
My answer is very simple, Kevin. It's how do I build extremely large-scale systems with large numbers of termination points and large numbers of components in such a way that I can keep growing it without essentially running into a barrier that makes it not work anymore, that makes it impossible for me to figure out how to get things from point A to point B. I'm going to run out of router table entries or compute power for moving topological information around or some other barrier. How do I?
That's actually the question. That's the layer of detail where the question is where you ask different people, you get different answers.
Okay.
And they will insist that the other person's answer is wrong.
I see. Okay. Well, stop. Let's stop there and find out what the answer from Paul Saffo. Right. Paul is an old friend of mine, and so I've imposed on him, basically dragged him away from what might have been a more interesting day to give us the benefit of some of his ideas and thinking. Paul, the little bio I have here doesn't mention Institute for the Future, but you were there for a long time.
I was at the Institute for the Future for a long time. I left there in 2006 and have nothing to do with them now
anymore. But now he's at Stanford University. But he's had all kinds of connections with the World Economic Forum. He's a columnist, a futurist. His opinions have been widely distributed and often appreciated. The thing I like about Paul, and the reason I wanted him so much to be here, is that he has a tactic for looking at the future, which I think is quite effective. He basically says, to put words in your mouth, you look to see where things are not sustainable anymore, or things that are trending in a direction where they're not sustainable anymore, and then you ask, what happens when they break? What futures, what outcomes might occur at those breakpoints? And I found that to be a really powerful organizing principle around which to think about how the future evolves. So, Paul, I'm hoping that you will make use of all of your various tools to help us see what might happen.
I'll do my best. Nothing like putting pressure on someone. And I'll do it quickly. It was interesting as I was thinking about, because this is my chance to get ideas from you all, and one of the things I'm obsessing on at the moment is some policy stuff around the economy. I just finished a paper talking very specifically about what it's no longer the next economy, it's the current economy, because I think the consumer economy we had for 50 years ended on September 14th of last year, and we're into something new. But I realized I've already written about it on the web, and if somebody's interested, you can find it. So why talk about that? I will make one plea. This is like pleading for Esperanto, and I know it. We desperately, desperately, urgently need a global micropayment system that has reach. I have no idea how to get there, so I just thought I'd mention that because you all actually know how to make stuff. And I can talk about it later if somebody's interested. Yeah, something. Well, I'll tell you, it's a distraction. So every talk should have a mystery. You can come back to it. What's the answer?
Using minutes on mobile phones as a medium of exchange.
It comes close, but not quite. Yeah, it's not quite global enough. I said it was like Esperanto. Here is something. I want to go back to a forecast I actually made in the earlier part of this decade. And as a futurist, I look back a lot. I'm here to tell you rear view mirrors are actually really good forecasting tools if you use them in the right way. And if you're going to be a forecaster, you better go back and look at your forecasts and ask yourself, what did you get wrong or what did you underestimate? And I have had this sinking feeling that something that I was thinking about and have been 5-10 years ago, I've underestimated what's going on by a very significant order of magnitude. A common problem. And we all do it in this business. So the background here is about every 10 years, a new technology arrives on the horizon becomes newly inexpensive and powerful, and then we find what the hell to do with it. So cheap microprocessors in the late 1970s led to the personal computer revolution of the 80s, and it was a decade preoccupied with processing everything we get our hands on. The personal computer was the poster child of that decade. We know that story. The next decade, the 90s, was shaped by the advent of cheap lasers, and it was an access decade. Profound shift away from devices defined by what they processed for us to devices defined by what they connected us to. And what made it possible was newly inexpensive laser diodes that started appearing in the 1980s. The poster child for that was, of course, the World Wide Web. The interesting thing about what we do is that we see the shift coming, but we always assume that the next innovation is going to be a marvelous accessory to what we already have. So remember in like 1986, the CD-ROM revolution, cheap lasers were going to give us optical discs where we go down to the computer store to buy and load onto our machines. And everybody else was walking around going, what are we going to do with all this optical, fiber optic bandwidth? Because we were thinking about laser-enabled bandwidth as an accessory to our personal computers. But what in fact happens is an inversion. The accessory becomes the central thing in the next decade, and the thing that was the center in the last decade becomes the accessory. So the shift from processing to access meant that the personal computer went from being the center of the action to the marvelous accessory to the network. So we have that inversion going all the way through. Well, we already know what the key technology of this decade is, and it's sensor technologies, which have been leaking into our lives. Cheap video cameras and, whatever. Pick your sensor technology, it's out there, whether you've got an accelerometer in your running shoe, Nike running shoe that talks to your iPod, whether, if you're like me, I almost got caught by the Sebastian Thrun's, Google Street Cam one morning because I was literally walking out to get the newspaper, and I saw it coming down the street. And I literally jumped behind a bush to miss it. Actually, it wasn't Sebastian's; it was the Microsoft one. I wouldn't mind if Google had me on it. Microsoft had problems being in their pictures. So remember, you're on camera. I know. I just nothing I wouldn't say on record. So the sensor revolution's here. It's happening. It's all around us. But the thing that has dawned on me in the last couple of weeks is, gosh darn it, I've done it again. I haven't realized how big this is. And sensors, think about how we think about sensors with the web and the internet today. They're marvelous accessories. They're an additional source of information. And I think we're right at that point. We're approaching a point where there's going to be a reversal, and the sensors are going to stop being the accessory, and they're going to become the main event. And I think the poster child of this age of interaction is going to become robots. You take a personal computer, you network it together, you use sensors to hang eyes, ears, and sensory organs on it. All you need to do is put wheels on the damn thing, and you got a robot. And there are robots everywhere. They've been around for a while. We had the Roomba iRobots device. The first person was killed by a military robot in February of 2002 in Yemen. And the Roomba is a good one because it actually, has anybody taken apart a Roomba? Yeah. It's not really a robot. Yeah. It's a bunch of electronics pretending to be a robot. But as a forecaster, it's an interesting indicator because way back in 2003 when this came out, I noticed a funny thing. I had a whole bunch of engineer friends here in Silicon Valley who were totally stoked about having a Roomba. And they were engineers. In my recollection, they had never owned a vacuum cleaner in their lives. And I noticed that they were giving their robots names. And I checked with iRobot, and they said, yeah, it's a really weird thing. 2/3 of our Roomba owners are giving their robots names, and 1/3 of them confess to having taken their Roombas on vacation with them. Or over to a friend's house. So as a forecaster, to me, that was a clear sign. Whatever was going on here was not about clean floors, and it's scratching a much deeper itch. So robots are slipping into our lives in all sorts of directions. There are 20,000 or so UAVs in the Iraq military space right now. And robots are now headed down the curve of Moore's Law. Quick example. Remember May 2004, the first DARPA Grand Challenge, 150-mile course, 21 entries. Most of the robots did what this one did. It came out of the Jersey barrier, looked left, it looked right, it thought for a second, hung a hard left, and died in the coyote bush 10 feet outside the fence. The robot that got furthest was Carnegie Mellon Sandstorm, here headed just, why did the robot cross the road? Well, to drive through a fence, which it did moments after I took that picture. And, of course, Sandstorm ended up, as the lower picture shows, a mere 7 kilometers into the race, stalled out on the side of the road, having burned out its differential because it lost where the road was. I was sitting halfway through the race with a bunch of folks. We were supposed to be doing support for the race, and we felt pretty stupid because there were no robots. So only 5 robots got any distance. The lead robot got 7 kilometers. Everybody looked stupid. Jump ahead 15 months, almost one doubling period of Moore's Law, and you have the second DARPA Grand Challenge. 5 robots finished. 22 out of the 23 entrants got further than Sandstorm got in the first race, starting to look like an S-curve. Jump ahead 2 years to the November 2007 Urban Grand Challenge, which my hat is off to the volunteers at that race. There were brave people in cars and pretending to be pedestrians walking around as these robots are going. Astoundingly, they had 11 finalists, 5 finishers. And it was a pretty damn impressive example of a race because it wasn't just distance. They also had to understand the vehicle code. Primitive as these robots are, an interesting coincidence that same morning proved something very important about the evolution of robots. 30 minutes before this race began, this is what happened 250 miles to the north, just outside of Fresno. Drivers driving through heavy fog, bumper to bumper, too stupid to slow down, had a 108 vehicle crash. It was 15 18-wheelers. I talked to one of the paramedics working this, and he said it was the damnedest thing. We were working on victims at the front of it, and we could hear the cars smashing in the back. People are like salmon in the fog. Well, what does this have to do with that? Well, this race, the Urban Grand Challenge, proved that robots, stupid as they are, already understand the California Vehicle Code better than 99% of Californians. And, of course, Sebastian Thrun has a forecast that half of all vehicle miles driven in this country by 2030 are going to be driven by robots. Here's the thing to think about. I think this moment relative to robots is like 1988, when everybody said, oh, lasers are really important. We're going to have CD-ROMs. And there were a couple of people running around waving their hands saying, no, that's a really stupid idea. We need a global ubiquitous hyperdocument system, that we can access everything in real time. I mean, remember how often we made fun of Ted Nelson. And we said CD-ROMs are the training wheels for that elaborate vision of the global hyperdocument system. And, of course, the web arrived just a couple of years later, and CD-ROMs never happened at all. I think we're doing the same thing with robots. And I think we're headed into a future where all of our estimations about the volume of information coming in off of sensors into the web is low by an order of magnitude. It's going to happen faster than we thought. The volumes are going to be greater. And it ain't going to just be sensors pumping information in. It's going to be sensors talking to other sensors. It's going to be robots requesting information. And I'm not talking about super intelligent robots. I mean, we've proven that stupid robots like the Roomba can win over people's hearts. But imagine primitive machines with some level of autonomy depending utterly on the web to communicate to other devices. And so that the web does the next jump of what has happened multiple times before. Remember a long time ago when most of the traffic on the phone system, I think we still have a phone system, I can't recall, but when we had a phone system, most of the traffic was voice conversation, and then voice became, below 1%, and the same thing's happening at the web today. We do not appreciate just how big a difference the arrival of autonomous machines is going to cause in terms of the demands for the kind of architectures and data flows and stuff on the web. And one what?
I can't figure out if I violently agree or disagree.
Microphone. Oh, and a wireless sensor.
I can't decide if I violently agree or disagree with you. Okay. Could you just define the term robot for me?
Perfect. Yes. So robot is, I have a very low definition here of robot. It's got some sort of processing power. It's got connectivity. It has the ability to sense the environment and ideally to manipulate the environment as well. Yeah, I think they're getting towards there. But the point I'm making is you're going to see these things, the Roomba is a very primitive device. It's not a robot in the sense that would frighten us all. But these things are moving up the performance curve a lot faster than I think we realize. Sir.
So why I listen to you, and I'm so with Deborah. There are pieces of it make sense, pieces of it I go, Now, one question I have for you is why you're making robots into these very distinct, stupid, independent things when all the trends I'm seeing with MEMS and other things say that, in fact, we're packing dozens and dozens of what you'd call a robot into something the size of a PDA within the next few years. So the answer is, other than an actuator to change its environment, at least the receptive side of it, the things that sense, that recognize what's going on around you or around wherever the thing is, it's becoming incredibly cheap. I mean, I'm sort of expecting to see a collapse of all of these inputs, at least.
Where I think all three of us are in agreement is that robots aren't going to look anything like what we all expected. In the same way that when lasers first came in the late 80s, all of our expectations were around CD-ROMs and electronic books and all that, and the way it played out was completely unexpected.
But that also is a good point, because it wasn't just the lasers. It was the termination technology for the fibers on the receive side. And so the next question is, what other enabling thing has to happen to unleash the robots that we should be looking at?
Why does it sound like Terminator 3?
Well, it's more fun that way, Vint.
My job here is to provoke thought. We could have a much longer conversation. I'd love that. Let me just leave you with one last idea. Maybe we do get, in 2 decades or so, we get really totally surprised that we actually get general AI. I'm agnostic on this subject. We may or may not, but if we should, and we actually get scary robots, I have a forecast. If we're very lucky, they will treat us as pets. And if we are very unlucky, they will treat us as food.
Wow. Okay. So before you get away, I'm going to make another kind of prediction. Robots? Where we're going, we don't need robots. I want you to think for a minute, all of you, not just Paul, I want you to think for a minute what happens when the network is truly ubiquitous, when every appliance and every device we have is networked. There are sensors everywhere. There are actuators everywhere. The ability to move around may be less important in some respects than trying to imply, and you may not have intended to, but one inference from what you said was that somehow the explosion doesn't happen until we have mobile devices that are participating. And I would argue that even without mobile devices, a network which is filled with sensors and actuators and the ability to both generate and absorb information is going to make a huge difference.
I completely agree. And again, because of the shortness of time, I don't intend to mislead. I agree. A robot doesn't need to have wheels. There's a definition around autonomy. The point I would take is, and it goes with what you're saying, the sensors no longer are the accessories. They become the main event. And the platform for wildcards. Think about Doug Lennett and the Psych project and all the attempts to create artificial intelligences. Maybe all those science fiction stories come true, and hanging all the sensors on the web give something in the net, enough awareness that, it happens by accident. I mean, I'm not saying it will. I'm just saying there's a lot of uncertainty about our assumptions here.
Okay, so there ended the formal interactions on this future topic. Let me find out whether you want to have some discussion with any or all of our last panel members. I see Andre and I see Kevin, so let's start running microphones around. Maybe it would be easier if we got Paul and Chip and Nick back up here, equipped with microphones, so we can have that discussion. We'll see where that goes for the next, say, 15 minutes or so.
A question to Chip.
There you go.
How does your work on quantum communication fits into the Genie project?
Grab the mic for a second.
I read your papers every once in a while and see that you are making progress.
Yeah, I spent, 5 or 6 years actively doing quantum communication and entanglement and teleportation. And I think the one thing that everybody agrees is that Genie is not a quantum network, which to my mind almost ensures that it will be, right? So just stay tuned.
Okay, other questions? Or Kevin?
I guess my question's almost a little related to that one, oddly enough, which is a little bit. There's a number of activities going on around the world, a bunch of money being spent, future internet, this, that. And if we look at how the current sort of internet got there, and we have the representatives in the room, it seems that there was a pretty relatively crisp vision of what to do, and there was an agency and funding to go get it done. And as the way I understand it, and you can correct me if I'm wrong, if you sort of didn't do it, you didn't keep going. It wasn't millions of flowers blooming. It was, we're going to go get this thing, we're going to interconnect it, we're going to make it work. So collectively, the future, if there is another future internet architecture or whatever it is that this name is being used in a number of research and development activities, is it going to come out of this investment in this direction, or is it going to come from some other place?
Let me give my view of the answer, and I think there are many different views. When BBN was part of Verizon was spending $15 billion a year on building out its part of the infrastructure. And in Genie prototyping, we're spending $4 million a year. So I don't think we're going to kind of replace what's going on. But what I do believe is we're in a planning phase where we're kind of milling about, trying to get a sufficient critical mass of people to say, yes, 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 we get it now. We want to do this. And that's going to take maybe a year, 2 years, that kind of time frame, where you could be doing all these different things. But you're going to get to the point where you say, we got it, and we're going to do this, and we're going to build it out. That's my belief.
I would agree. I think it will. There will be a bunch of ideas that will come out of that, and just like, because there's already an internet, the chances that everyone sort of latches onto one right early on, to sort of that seems no longer possible, but that there will be a handful of good ideas that will just get adopted and used, and then it'll be the sheer weight and buying power of people like Google and AT&T and Verizon, and that will just, if they're good ideas that they want to take and run with, then they are the ones that will make it happen. And so in some ways, it's like the ultimate transfer of technology. Right?
So could I jump in for just a second and try to amplify, respond to Kevin's question? One of the things that we could see happen as the internet evolved was that when we moved away from router defined by a computer with a graduate student wrapped around with his arms around it, that's what routers were. They moved in, as soon as they moved into a more commercial setting, the set of people who understood things about routers and were free to try new ideas out was reduced in some sense, or at least confined in a proprietary environment. It's a little bit like the early stages of VLSI, where you had to know a lot about the physics of the material and process before you could put an integrated circuit together. When Carver Mead and Lynn Conway put their ideas together for VLSI design that removed dependence on the underlying production technology. A large number of people learned how to do VLSI design. So it's possible that what Nick is suggesting, and I think what Chip is suggesting, is that we might reopen opportunities for people to learn more about and experiment with stuff at very low levels in the architecture of the network. There was a whole generation of people who didn't get to do that as the network became a commercial entity. And so there may be, I don't know for sure whether that will naturally cause, some interesting thing to happen, but it feels like it opens up an opportunity that we didn't have before. Part of the driver that made internet successful, I think, were some fundamentally new ideas, one of which was packet switching, and the other one was that networks should be able to be federated, that it didn't have to be a single uniform system, that multiple parties could build their own networks and then had a kind of organizing principle that allowed them to be interconnected. If we discover different and maybe better organizing principles, we might end up with something dramatically better than the internet. And it's opening up the opportunity to explore those possible alternative organizing principles that might help. Some of the things you're doing, Kevin, for example, when you play around with the address space and the namespace and the ability to be more flexible about that, are pushing in directions that the current network struggles. Go ahead.
Well, I was just told two other people were ahead, so I'll wait. I was going to comment on your VLSI point later.
Well, my question's a little off base. It's about the future of energy. And what I wanted to ask you guys about was your opinion on the computer scientists that are now saying, let's take an internet approach to kind of the grid and the future of energy management and all this kinds of thing. And I'd just like your thoughts on that thinking. Does that sound correct to you? Does it sound like that kind of, the approach might work, or is that just off base?
I guess I'm supposed to answer. Let me offer you some data points, because I think the fact that people have been thinking about that is really interesting. Because I think it's a subset of a couple of things. It is showing the influence of, we're right in the middle of a shift from an information-centric, electronics-centric view of the world and shifting to a biocentric view of the world. And so you start seeing people looking at the electrical grid, not just in terms of the internet, but saying, are there biologic models for how this works? And it's leading to people talking about energy generation differently. 3 examples. My good friend Stuart Brand has a book coming out. Stuart Brand, Whole Earth Catalog, top environmentalist. In the book, he's making a strong case that we must use nuclear power, which is going to shock his environmentalist friends. Then you have other people looking at solar saying, wait a second, at the rate solar installations are doubling, it'll only take 8 doublings before solar collectors can deliver all of our energy. But that's a distributed system, and it requires a new kind of distributed architecture. And then you have the third set of people saying, well, if we're going to have solar, if we're going to have distributed, how do we store energy? So there's a retired scientist from Lawrence Livermore Labs who's saying we need to create a whole new kind of battery for solar, because today's power batteries really, at the level of what we're talking about for electrical power, only store for, 3 to 6 hours or so, even if you're talking about fancy supercapacitors made out of unobtainium. And so he said, well, why don't we come up with a new catalyst to more efficiently split water using electricity to generate hydrogen to make natural gas, and the natural gas you create is the battery that you then feed into the existing natural gas distribution system. So I mentioned those 3 examples of everybody in the energy space is starting to flip backwards on their assumptions. Environmentalists are saying we need nuclear. Centralized people are saying we need distributed solar. Other people are saying we need radically different approaches to batteries. And underneath all of that is an electrical system that is vastly more heterogeneous than it is today. It's not a monoculture of power stations, and it's going to need a radically different kind of architecture. So the folks working on that, it has the smell of inevitability.
Okay, where else? All right. So thank you. So actually, this is good because it's following up on the energy question at some level, and it's coming back to Vince's point about VLSI. And Vin pointed out that in the VLSI programming, it was when we managed to abstract the physics fast enough that somebody could deal with it in a digital world more conveniently. And it seems to me that one of our crashing problems, and I'm going to be interested to know how the guys up front feel because they've been dealing with some of it, I know, with quantum from Chip and so forth, that the issue is we seem to be running to lots of places where we have to program physics. We are running to a situation where suddenly we need programmers who understand the physical world that they're trying to program because the sensors give them actuators in the physical world. In wireless, I mean, you talk with Vanu Bose, and the number one thing he says is, I can hire a computer scientist, and it takes me 18 months to teach them enough RF physics that are useful to me. I hire an RF physicist, and I have to spend 2 years teaching them enough programming that they're useful to me in dealing with the software radio. Similarly, in the energy environment, at some level, when you start building more sophisticated distributed control systems for energy, you have to start understanding what goes on and the fact that I'm told I know very little about the energy system. There are insane nonlinearities that start to show up. You sort of tip a tiny bit and suddenly everything goes ape wild. The current starts running the opposite direction or whatever, nifty things start to go on the different power circuits. How are we going to deal with that? Are we going to manage to find new digital paradigms? Because it's very hard to teach a whole lot of people to do analog programming. And where are they going to come from?
Actually, I'd like to respond to that and say that you're right on target. A number of people who teach electrical engineering have told me repeatedly that people come in who are perfectly good at designing logic circuits, but we're down at, the sizes of the circuits are down at the point where quantum effects are an issue. They haven't the foggiest idea why stuff doesn't work because they don't understand the physics of it. They don't understand the analog world. And that's a huge issue. And in fact, it suggests to me that there's some serious opportunity here for, educational curriculum reform, if nothing else. It also suggests, Craig, that there needs to be a real effort to tear down disciplinary barriers. I now hate the word disciplines, not discipline, but disciplines, because it implies that things are segregated, and we know they're not, and they're becoming more and more conflated because of the places where we're operating, either in the ultra small or the ultra large. So your question, I don't have a good answer for where are they going to come from, except for the fact that we got to start thinking about what people should be learning in order to be ready to do the right things in the next 10 to 15 years.
And one problem is that we look to the universities to do that, and to some extent they're wonderful at accomplishing it. On the other hand, they are the most conservative, slow-moving, bureaucratic organizations, and so you think that computer science departments didn't really exist 30 years ago. It was in that time frame. But do you imagine getting rid of them now? I mean, they're there forever, even if they don't make sense anymore, right? And and what's happening with electrical engineering and computer science departments is that they are being forced right now to rethink their existence, their curriculum. I think it's wonderful. And our own departments have been doing it, but clearly it's happening at every school. Real rethinking of the curriculum, because I think everyone knows that there is a problem of which you speak. Is it's not enough to teach someone how to do logic design plus a little bit of low-level programming anymore and call them an electrical engineer or a computer engineer. You need to give them access to be able to learn those new skills very quickly and familiarity with them, and that really will transform the curriculum. And I would bet that no one's got it right yet. We're going to see a real big transformation in the next few years.
I think it's a good place for me to stop. I don't have a question.
I'm getting a strange sense of deja vu in part of this conversation, especially from Craig's remarks, because I remember hearing the story in the 60s about whether one should hire people who could do numerical analysis or people who could program computers, and which was easier to turn into the other one. And we heard issues about modeling and whether it was easier to hire somebody who understood the insert field and teach them about the computing, or hire somebody who knew about the computing and so on. So this is an old problem with or without the presence of computer science departments, which I agree may contaminate things further. The other thing I'm hearing in pieces of this conversation and would like some thoughts on is the echo of Wiener claiming that digital computers were really going nowhere, and he never really got digital computers, and was basically claiming that when we started getting to what we would now describe as the limiting end game of this digital stuff, we would be back to discovering analog computing, analog processing.
No response. That was a provocative. Come on, Paul.
The only thing I would say is I completely agree. Sensors are analog devices, and when they started appearing, I mean, when MEMS came onto the radar, no pun intended, in 1992, 93, everybody started asking the same question. And if you think about, in my rather inarticulate way, what I was trying to say is this moment relative to sensors is the same as 1988 was relative to the arrival of lots of optically enabled bandwidth, and we were all scratching our heads and had the sense that something big was about to happen, and all of our forecasts were wrong, and the thing we thought that was really far away turned out to show up in the early 90s, and the thing we thought that was right there, CD-ROM, never really showed up at all. I think the same thing happens with sensor technologies, and not only in terms of its impact on how we use the network and how it affects our lives, but how we think about this relationship between digital and analog.
I think that's right. I just think when you go to say in the answer,
microphone.
I think all that part I'm fine with. When you go and then say, and the thing that this time we are going to predict right is robots. The problem I have with it is that's only true if you define robots to be so general, and that I'm not sure why we're using the term robot.
Agreed. Two thoughts. One, I think robots will be nothing like anything that we imagine today. The second point in my defense is, and I'm sharing an idea here in the spirit of this meeting that is not a complete idea. And then the only other thing I would say is recalling Herman Kahn, who in the early 60s wrote in the front of one of his reports, warning, portions of this report are intentionally misleading in order to provoke thought. In this case, I'm being unintentionally misleading because I don't have the answer yet myself.
Tony.
One of the things I love about coming out to the Valley is basically hearing a future of the way things could be ideally. Most other venues are decidedly not quite so upbeat. So I'd be curious to hear if each of you describe the worst case prognosis for the future, and maybe what we will actually see is somewhere in between.
Mm. Well, I can certainly tell you what my worst case scenario is with regard to the internet. It gets locked up. The incumbents control everything. They succeed in avoiding net neutrality and non-discrimination. They become the sole suppliers of access to broadband facilities. They throttle innovation. They prevent competition for higher level services. And we end up with a kind of wasteland where the access to the internet and its applications are kind of like television. They're channelized, they are monetized, they are controlled in a way that simply stifles any contribution coming from the general public or from the universities or anything else. It would be the antithesis of the kind of future that I would like to see evolve. Chip.
Let me give you my Genie version of the nightmare, which is Nick and other people working on Genie build a beautiful infrastructure on which people could do experiments and research, and no one has the desire to do it. I really, myself, personally feel the American education system is having a lot of troubles. We've never been particularly interested in education in this country. And I don't think the level is going up. So it really could turn out quite badly if we spend a generation or so not really training people how to build these systems.
So, and mine's going to be a little bit more like Vince, sort of five things. One is that I fear what the centralization of data means, because it's I feel as though we are all giving up something by the centralization of our data and the loss of control that we have over it. The second one is that once we have lost control of our data, we lose control over how we process that data, and the services and applications that we run. And I'm hoping that right now is we're going through a temporary phase where someone figures out how to do that.
Could I just as a visitor, I come into this complex and notice that you have a statue of a Tyrannosaurus Rex and a shark fin. What if Google went bad?
Yeah. So I think that's worrying. I think that something will happen to reverse that fear. The third one that I worry about is very similar to what Vint was saying, is that the closed walls of those who own actually the wireless infrastructure will keep those walls closed, and that whereas as I sit here and we all sit here, there is huge amount of wireless capacity around us from many providers, Wi-Fi, several operators, that I can't harness it all. Why can't I harness all of it? Why can I only harness one at a time? Why can't I harness 7 of them at a time? Why can't I harness many of them at a time and use that? There's not a capacity problem. It's a contractual problem. It's walls that are built there. Why can't I connect to 5 or 6 of them and 5 or 6 Wi-Fi at the same time? And the fourth one, related to what saying earlier, I fear that the network infrastructure will stay fixed and closed. I think that we have to say the emperor has no clothes, and that we've allowed it to stay ossified, and that needs to change. The fifth one, a little unrelated, is there's sort of many talks, like I'm sure you have, where people say, this new technology with GPS built on it, these handheld devices, it means that when I walk up to someone at a party, we're both going to see something on the screen that tells us what we have in common. And one of the things that actually I fear is that we will forget that it's fine just to walk up to someone and say hello. And are we going to be driven by our geekiness to sort of forget ourselves? Right? That worries me too.
Paul,
I'm just so grateful we all gave up trying to beam our business cards to each other with our palm. So I'm with you. Pessimism is the new black, and so there are all of these apocalyptic scenarios. And as a forecaster, I love collecting these things. My favorite one at the moment. It ain't going to happen, I can promise you, that there are a bunch of people who believe that the end of the Mayan calendar is in 2012. And I can state with some authority, I used to be fluent in Maya. I actually worked on Mayan hieroglyphs. I can count in modified vigesimal. So I'm a sophisticated consumer of the experts in the field. And these superstitious folks have it all wrong. But their nightmare is it's going to coincide with the peak of the next solar cycle, which should start up in the next couple of months, and we'll all be screwed. So that's the negative one. Let me give you the middle range forecast. So I actually think this will happen. This is a likely outcome. It's not hell, it's not heaven, it's not cyberspace, it's not cyber hell, it's sort of cyberbia. This world of imperfect networks and information, we all worry about losing our data. Famously, I forget who said it first, it wasn't me, said information in digital form lasts forever or for 5 years, whichever comes first. So we all worry about losing our data. I'm with you about the cloud, but here's my forecast. We're going to end up inevitably in a world where we will, in fact, lose the information we most want preserved. But it will also be a world in which the information we our colleagues and when our children can't find what we want and we can't shed what we really hope would go away.
Wow. God. Okay. Last comment.
Last comment. I spend my time in a lot of international fora where the few U.S. people who are there basically advocate Vince's worst case vision. Who's also there are lots of brilliant, innovative PhD young people from China, Korea, Japan, who are looking for innovation leadership from the United States. And it's not there. So I think one of the things we need to think about as we leave is taking all this kind of marvelous vision and creative energy and realize that this is now a global business, if to the extent anyone wasn't aware of that, but that it's decidedly less U.S.-centric. And think of ways basically to engage and to be effective on a global scale with all those others that are out there that are yearning for this kind of creative interaction.
And Vint clearly needs to fly more if they're lacking in leadership over that.
Thanks a whole lot, Paul. Okay, I see you have a microphone. Did you want to make a comment?
Yeah, I just wanted to just point out that what's great about the Valley is that we're irrationally optimistic, and I hope we don't start thinking about like worst case scenarios, because it you know, instead of just talking, we're just doing. You know, when two graduate students like go and say, oh, we're gonna organize the world's information, it's kind of you know, it's irrational, but they went ahead and did it. So I think it's good to keep like, you know, just thinking positive. But I had one comment to Nick, because in your presentation you mentioned, I mean, the status quo sounded like, you know, 90% overhead that you have to pay to Cisco or other companies because of like that, you know, those 20 million lines of code that you have that like, you know, probably like very few people are, you know, taking advantage of. And I wonder if that kind of like, you know, that kind of like disruptive technology that you want to implement should be, you know, competing based on price, because that was the, you know, at the beginning of your presentation, you talked about the fact that like, you know, 90% of the money was just being lost on like, you know, that code, that overhead.
I think that just means it's inevitable. The fact that, you know, the underlying hardware costs, you know, I don't know what the right number is, but 10% of what that just means it's just a question of time. If you're looking for cracks in the wall, there's a crack that it'll just open up, and it's already opened up, right? So that's in the process of happening. I don't think that's necessarily the reason to do it, but that just makes it inevitable. What will then happen on top, hopefully, is that once that has opened up, that you get that power of that open source or developers community that will innovate on top. But I don't think that price alone is the right reason to do it. It just means that it's not sustainable, right? So the comment was, you look for those things that are not sustainable, they won't, therefore they're not sustainable. And so what happens when they break down? And I think it's just one that's just waiting to happen. To some extent, I think it already has.
Are there some applications that you're thinking about that would be enabled by your architecture, like, you know, at the top layer?
Sure, we could. I mean, I don't want to disrupt time, because I mean this could take. We can talk about this offline, but yeah. So I'd be happy to. I mean, before I leave, happy to spend some time to. One thing I actually want to get. Can I just say one last thing about the education, and that is that as like many people in the room, as a non-American, that I think that thinking about it as American leadership has often been wrong, and I think it's still wrong. That the leadership that we think of as being American is a combination of American-born and trained, plus an enormous ability to harness those people that come here, and that leadership that is yes, it's physically located here, and that actually one cynical way of thinking about it is we don't necessarily need a great education system here. We just need to be able to keep attracting as many people as possible. So I don't look with so much gloom and doom at the K through 12. I look with more gloom and doom at the college and above, because it's still a phenomenal magnet. I mean, the U.S. maintains how many of us would consider living anywhere, of those that live here, how many would consider living anywhere else, right? And I think that will continue to be the same. So I don't think it's quite so scary.
Okay. All right. Carla reminds me there are several things that we need to do. First of all, let's thank the panel. Thank you. You may stand down. Second, I want to make sure that we all show our appreciation for Carla and Denise and all the hard work that they did organizing this thing. So where's Denise? Denise is not here. Well, she'll get to see it on the camera. Oh, there you are. I'm sorry. I didn't know where you were. All right. The last thing I wanted to do is to borrow another quote from my friend Doc Brown. Because we've been talking about the future. And if you remember the Back to the Future 3, where the paper is blank. And the reason the paper is blank is because the future hasn't been written yet. That's your job. Okay, end of meeting.